All right, let's dive right in. Today, we are pulling apart the atom. I mean, this is the fundamental building block of, well, pretty much everything in our universe. So let's go ahead and open up the blueprint.
So, let me ask you something. Think about yourself, the phone you might be holding, the air in the room, even the farthest star you can see at night. What on earth could possibly connect all of those things? The answer, it turns out, is kind of amazing.
That's it. It's all built from the exact same tiny set of parts, just, snapped together in different ways. And today, we're going to pop the hood on that blueprint and see exactly how it all works. Okay, first things first. If you want to understand how something is built, you got to know what's in the box, right? And for the atom, that parts kit has just 3 fundamental pieces.
So here's the basic model. You've got this dense core right in the middle. That's called the nucleus. And then zipping all around it, you have these things called electrons. Now inside that nucleus are our other 2 particles, protons and neutrons. Let's meet them one by one.
First up, we've got the proton. Just think P for positive. This guy is one of the heavyweights, and it lives right in the atom's core, in the nucleus.
And next to it is the neutron. And just like the name sounds, it's neutral, no charge at all. It's basically the proton's roommate in the nucleus, and they're about the same size.
And finally, there's the electron. This one's completely different. It's super tiny, it's got a negative charge, and it's just buzzing with energy, constantly moving in that huge space outside the nucleus.
You know, we say the electron is lightweight, but this really puts it in perspective. It's not just a little bit lighter. The protons and neutrons have practically all the mass of the atom. It's crazy.
And this one is even more mind-bending. All that heavy stuff, the nucleus, is like a tiny marble in the middle of a giant stadium. The rest of it? That's just the empty space where those little electrons fly around. An atom is mostly, well, nothing.
Okay, so let's do a quick recap. We've got our 2 heavy particles, the positive proton and the neutral neutron, hanging out in the nucleus. And then we have the tiny negative electron zipping around way on the outside. That's it. That's our entire kit.
Now that we've got our parts list, we need to talk about the single most important rule in this whole construction project. This is the rule that gives every single element its unique identity.
So here's the deal, and this is absolutely crucial. The number of protons is everything. It's called the atomic number, and it's like the atom's permanent, non-negotiable ID badge. It's the one thing you absolutely cannot change without turning the atom into something else entirely. Seriously, it's that simple and that absolute. If it has 6 protons, it is carbon. Period. No exceptions. If it has 79 protons, congratulations, you've got gold. The proton count is the only thing that defines what an element is. And this comparison right here is the whole ballgame. If you mess with the number of neutrons, all you're doing is making a heavier or lighter version of the same element. But if you change the number of protons, you've basically performed alchemy. You've created a totally new element.
Okay, so we've got the main rule down. Protons equal identity. So, what happens when we start playing around with the numbers of the other 2 particles? Well, that's where we get some really interesting variations.
So, like we just hinted, changing the number of neutrons won't change what the element is. But it does create a different version of it. So, what do we call that? You get an isotope! Yeah! Isotopes are just part of the same element family, right? They just have different weights because they're carrying a different number of neutrons in their nucleus.
A perfect example is carbon. Its identity is locked in, right? It's got 6 protons, but it can have different numbers of neutrons. So carbon-12 is the one we see most often. It has 6 neutrons. But if you add one more neutron, you get carbon-13. Still carbon, just a little bit heavier. They're just isotopes of each other.
All right, so we've messed with the neutrons. Now let's see what happens when we change the number of those speedy little electrons whizzing around on the outside.
Well, then you create an ion. See, in a normal neutral atom, the number of positive protons is perfectly balanced out by the number of negative electrons. But if you upset that balance by adding or taking away electrons, the atom isn't neutral anymore. It becomes charged.
Let's look at this sodium atom here. It's got 11 protons, which means it also has 11 electrons to keep things balanced and neutral. But I want you to notice that one little electron all by its lonesome in the outermost shell. It's kind of hanging out there. So what happens is, if that sodium atom loses that outer electron, it now has 11 positive protons but only 10 negative electrons. The positive charges win. The atom now has an overall positive charge, and we call it a positive ion. It's like the old joke. One atom says to another, "I think I lost an electron." The other one says, "Are you positive?"
So we've seen how to build an atom, we've seen how to create different versions of it. But why does any of this actually matter in the real world? Let's zoom back out for a second.
Because this stuff isn't just theory. This is what runs our entire world. When that sodium atom gives away an electron and becomes an ion, it can bond with a chlorine atom to make table salt. That's the foundation of all of chemistry. And those isotopes? We use the unstable one, carbon-14, like a cosmic clock to figure out how old ancient fossils are. From medical scans to tracking pollution, understanding this blueprint lets us literally read the history of our planet and build its future.
And that kind of leaves us with one last big thought. If everything, gold, carbon, the oxygen we breathe, if it's all made of the exact same 3 building blocks, just in different amounts, it really makes you wonder, what are the limits here? What kind of unbelievable new materials and technologies could we design if we truly master this universal blueprint? Just something to think about. Thanks for joining me.